Okay, I think we'll get started. Good morning everyone. So very happy to welcome you here to the Climate and Energy College at University of Melbourne. My name is Roger Dargaville. I'm one of the supervisors here at the college. I actually work at Monash University now. I used to be here at Melbourne, but I'm still finishing up with a few PhD students in the meantime. So today we're here to hear from Graham Palmer, who's going to give his completion seminar for his PhD on the topic of the energy return on investment work that he's been working on for the last few years. So Graham's been an absolute pleasure to have as a student. He's obviously a little bit older than the average PhD student. He's got a lot of experience under his belt already before he started his PhD, and was very driven with what he wanted to do, had a very good idea about what he wanted to do, because before he even started his PhD, Graham had written a book on energy transitions, and he's very fascinated by the history of energy and how we've gone from being a society based on sort of hunter-gatherer, basic agriculture, to being the economic powerhouse that we are today. So Graham's going to be talking about the energy return on energy investment problem. And just to give you my take on that as you know, one step in helping to warm you up the idea, we're probably familiar with the idea of producing bioethanol from corn in the United States. This is a subsidized activity. And if you do the calculations, depending on your assumptions, it actually turns out that there's more energy required to produce a litre of biofuel from corn than what is actually contained in the fuel, and yet it's an economically sensible thing to do. So this is an example of where, if you just use the economics to decide whether you should undertake an activity, you would say, yes, you should. But if you take a step backwards and do the energy fundamentals, you would say, actually, there's something wrong with this. And the economics are obviously playing funny buggers with the situation. So Graham goes into an awful lot more detail in this analysis, and rather than looking at biofuels, he's focusing on the electricity sector, which is again an order of magnitude more complicated. But with that, I will hand over to Graham, and Graham's happy to take questions as we go, but otherwise he'll speak for about 40 minutes with time for questions at the end. Okay, thanks Graham.
Thanks, Roger. Good morning, everyone. Before I start, I'd just like to acknowledge the traditional owners of the land, the Wurundjeri people, and pay respect to the elders past and present. I've also got a few acknowledgements. Thank you, Roger. You've been a great supervisor. Unfortunately, David and Robert couldn't make it. There's lots of other people that have helped along the way too. Josh Floyd, Charlie Hall, Kerry King. And of course, Malta and everyone at the college, thank you guys. And Kylie, Lachlan and Sarah. My daughter Sarah's here today, so. So I'll get started. First of all, I'll contrast the standard economics perspective with a biophysical perspective. EROI fits in with a biophysical perspective. And because EROI is considered heterodox from an economics point of view, I'll spend some time framing EROI within the framework of the standard economics model. Then I'll jump into my research aim and method and give you a clearer idea of where I'm going. I'll identify some of the challenges. Then I'll move into some of the studies that I've done, including an environmentally extended input-output analysis of the Australian electricity supply industry. I'll look at a consequential life cycle assessment that I'll explore in more detail. Look at another study I looked at where I look at a divergence of results and why that divergence comes about. And I've got a bit of material here. I'm not sure whether I'll get time, but I'll link energy and productivity used in Australia as a case study, which will link in with the final paper that I did and bring up some conclusions. So this is kind of economics 101. Economics is considered a circular flow model. Producers or firms produce things, consumers buy them. There's a flow of money. And then producers send income back to consumers. Now, national accounts are produced using this circular model where it's based on double entry bookkeeping in effect. So GDP is equal to the sum of all expenditures or all income. And this is a really neat model. It works really well. And this is sort of the way economics is always framed. And within that, I put energy supply. One of the interesting things about energy supply as a proportion of total economic activity is that there seem to be cost share thresholds. So in other words, in OECD countries, if the share of energy expenditures as a proportion of GDP is below about 10%, everything runs well. But above about 10% leads to economic contraction. And I'll sort of discuss that and come into that a bit more. One of the basic assumptions of this model is that the whole system grows because of total factor productivity. Total factor productivity is not measured directly, it's a residual. So it's measured from what's left after you account for capital and labour. It's also called technical change. Basically, it's assumed that technological change drives an increase in growth. So per capita GDP is assumed to increase because of technological change. I'll come back to that. Now, ecological economists say, no, look, it's a bit more complicated than that. We have energy and materials entering the system. We have waste and pollutants exiting it. But the standard approach to this is to consider these things within the framework of that standard model. So in other words, energy extraction is simply the capital and labour used to produce that energy. And waste, while we make choices about what we do, we might tax waste, we might regulate against waste and so forth. But everything is within the framework of that standard model. So to understand energy return on investment, it's necessary to look at the linear flow model. So from this perspective, instead of everything being circular, we get primary energy from nature being processed by energy supply industries, delivered to industry and households. Now, one of the interesting things about standard economics is that there is an assumption of equilibrium. So an economy will find a state of equilibrium. This is sort of economics 101. But from a thermodynamic perspective, the economy is in a state of disequilibrium. As if we consider sunlight, for example, the planet would basically stop without sunlight. There is no equilibrium as such, or the state of equilibrium would be death. Now I'll introduce a really important factor in energy return on investment is energy industry own use. So this is the energy that the energy supply industry uses to basically process the energy from nature. And this is a key metric, and I'll just go to my next slide. So EROI is simply defined as the energy out divided by that energy industry own use. And it is conceptually, the inverse of this is conceptually the same as energy expenditure cost share as a proportion of GDP. So one of the first things that comes out of that idea is that the EROI has to be much greater than 1-to-1 for a society to basically function, or for our society to function. An advanced society needs something like an EROI of 10-to-1 or greater. So in other words, if an energy supply technology is much less than 10-to-1, it isn't able to support an advanced society. There's a whole bunch of other things that I could sort of say about this, but I'll have to move through. I'm sorry, I've got some notes here, but I'll keep moving through. Well, one thing that I probably should note, if I go back here, prior to the age of fossil fuels, basically sunlight powered everything, and it was sunlight in real time. Essentially, since the age of fossil fuels, we're using stored sunlight. I looked up the other day, 1 litre of petrol is equivalent to something like 25 tonne of waste vegetation. So 25 tonne, it's quite an incredible sort of figure. So we're basically using what are effectively millions of years of stored sunlight in a very short time. The effect of this is that this is the main driver of economic growth. This is sort of how we have come to be where we are. But of course, we need to work out a way post fossil fuels. So I'll move on. So the key question is, how do we calculate this figure, energy industry own use, because it's it's basically a simple idea, but it's quite difficult to actually calculate it. And so my thesis aim is address the methodological inconsistency of electricity-based EROI studies, because it turns out it's very difficult to measure this in relation to electricity, mainly because electricity is a real-time system. It isn't like, say, oil, where you can put oil in a bucket and carry it somewhere. Electricity is only valuable within the context of a system. So key points up to now. So the EROI ratio provides an energetic valuation. So at this point, we can't just simply abandon the basic economic system that we have. It is really useful, and a lot of things, our lived experiences at costs actually matter. And so in normal sort of day-to-day activities, we normally just consider costs. But in cases where the EROI is quite low, then the energetic valuation may actually be much more important than what other costs. And part of the aim of my thesis is to try to combine those two ideas so that we understand both the economic valuation and the energetic valuation. So nearly all energy economic models adopt standard economic assumptions. So this includes integrated assessment models used in the IPCC, energy optimization models, and so forth. They assume a closed system model in equilibrium. Per capita GDP growth is due to total factor productivity as a result of technical progress. So I've already covered this. The inverse of EROI is conceptually equivalent to energy expenditure cost share, and so that's a really important point. One of the interesting things about EROIs is trying to work out what is the minimum EROI of society, and a lot of people have sort of put a lot of work into that. With our current configuration, it's estimated to be something like 10:1. Agricultural societies could thrive with much lower, but they are much simpler societies. Basically, when everyone's a farmer, you don't need a high EROI. And one way to frame EROI is it provides a quantitative estimate of the competition between resource depletion and technology. So this is a really important thing. A lot of fossil fuels, particularly oil, the trend is towards resource depletion. It's harder to extract oil, it requires more energy. On the other hand, some technologies are improving, particularly wind and solar, and EROI provides a way of understanding that sort of competition. So this is my research method. For those of you just starting, I didn't do this research method the first week of my thesis, so this took a while to sort of put together. EROI is based on life cycle assessment. That's the way that we work at energy industry own use. Now, one of the things I wanted to do was work out what I was going to work towards in the end, and I decided to work towards how to endogenize EROI into integrated assessment models. And so that was sort of my end point. Actually, if I use this. And so what I did is I started off with a demand-based consequential LCA. These are probably terms you're not familiar with, but most EROI analysis are done with what is called a process-based LCA, and there are a few problems with this. The first one is that they are incomplete, and if you're just trying to look at how much energy it took to produce an energy technology, they provide a sort of a useful picture, but they don't provide a complete picture in terms of understanding how an energy technology will support an energy transition. One of the key ideas of my research method was to approach the problem from a top-down and a bottom-up perspective. So my top-down perspective was an input-output analysis of the Australian electricity supply industry, and I'll go through that. Bottom-up is a more technology-specific, so trying to look at things more at a kind of a project level. And then my final paper is actually taking all of this and trying to develop a model of how to endogenize EROI into integrated assessment models. So this is some of the issues that we come across with trying to do electricity EROI. The first one I just mentioned, the study goal of energy payback is sort of a traditional goal that goes back to the 1970s. People had realised that the amount of energy it took to produce a solar panel in the 70s was quite high, and it may have been commensurate with the energy that that panel would have actually generated over a lifetime. And so this was sort of the framing, the idea of energy payback. And as technology improved, the energy payback may have gone from, say, 25 years to 20 to 10 and so forth. And so this became the way that EROI was framed. Rather than trying to understand EROI in terms of what that technology contributes to an energy transition. And this is sort of a really important part of it. Most EROI studies are done using a process-based LCA, which one of the main issues is truncation error. In other words, 30 to 50% of the energy inputs are not included. Whereas input-output analysis is a systematically complete method of doing an LCA, but it has the problem of it assumes it assumed homogeneous flows between different industry sectors, which I won't go into here. Another issue is that EROI studies have virtually all been related to generation, but of course there's transmission and distribution, and there's the whole lot. And really it needs to be understood, EROI needs to be understood within the context of a whole system and what it contributes to a system. Age of primary data is a big issue. There was one paper that came out in 2016, Ferroni and Hopkirk. They'd cited a paper from the early 2000s, and that paper from the early 2000s had used data from the late 90s. And so this is a real issue that you're looking at a paper from 2016, and actually the data set is from the late 90s. And so you need to be aware of these sorts of issues because they came up with a very low EROI, not surprisingly. An issue is temporal displacement of energy. So that simply means that we have to put, with a lot of technologies, we have to put the energy up front to build something, but the energy accrues over a lifetime. And how do we think about that? Do we discount energy? How do we do that? Energy equivalence is a big issue. It's sometimes called the IEA versus EIA or BP issue. Basically, electricity is a secondary carrier, and if we want to know the primary energy that went into electricity, we need to know what actually generated the electricity. And there are basic conversion factors. With electricity, generally there's 3 thermal megajoules that produce 1 electrical megajoule. But it doesn't always work this way, and depending upon your study, you can end up with dividing your result by 3 or multiplying it by 3, and you can kind of get really anomalous results unless you really understand that. Basically, because most electricity has been generated by thermal generation, thermal equivalence has been the standard. But of course, as we shift away from thermal generation, we need to understand how do we account for energy equivalence. And electrical storage is an issue, and I'll discuss that a bit more. So my first study, which is a top-down study, I wanted to calculate the EROI of the entire Australian electricity supply industry. So what I did is I took the ABS produces input-output tables. There's 114 sectors. Essentially, they produce 114 by 114 matrix of flows between energy sectors and final consumers. I took energy data that was available. It doesn't align precisely with the ABS data. And I produced a environmentally extended input-output analysis. Now, unfortunately, the resolution isn't good enough to see all the data, but basically, if we start on the left there, these are primary energy extractions from nature. And one of the important things about EROI is that we don't differentiate between fossil fuels. For example, this is that's black coal, brown coal, kinetic energy in wind. This is sunlight, natural gas, and so forth. So from an EROI perspective, they're all treated the same, or of course, the emissions are completely different. These are end use, industry and households. The red lines is electricity. These are the particular industries. We've got generation is all of these. Then we've got transmission, distribution, on-selling and retailing. The width of these are basically proportion to the amount of energy. I mean, one of the things that you probably note is that if we look at black coal, for example, that's the energy that goes in and you get that much electricity out and that much waste heat, for example. These small lines are the lines that I'm interested in. They're the energy expenditures by the respective industries. So, for example, with coal mining, it's the diesel used to run the tractors and so forth. It's the electricity for milling and so forth. One of the things that input-output analysis does is it takes all of the economic data and allocates an energy intensity to that. So that what it enables us to do is look at the entire embodied energy picture of the entire industry. And so, I'll get out of the way. So I came up with a figure of 40:1, which is actually really high. And in a way, it's kind of not surprising. Like if you think about the amount of diesel use by coal mining, you get a lot more coal. And this provides a sort of a starting point, a reference point. But it's really important because there's a lot of electricity supply technologies that are a lot lower than this. So the situation is, well, how do we reconcile that? Another study I did was a bottom-up. So I wanted to evaluate the EROI of electrical storage. One of the problems in the literature is that there's been a lot of work on this, but it's been very arbitrary. People haven't known how much storage. There was one paper by Weissbach that looked at solar and they assumed 10 days of storage and 2 times solar overbuild. And they came up with a very low EROI, which is sort of not surprising. So what I wanted to do was come up with a methodology that provides a consistent framework for comparing like with like. Because that type of study, I mean, you could in theory do that, but nobody's planning on doing that. It doesn't make sense. Now, one of the way I approached it was using electrical reliability indices. I contacted an engineer in Texas who works on the ERCOT grid. He's a reliability engineer and he provided some of the equations. Now, this is a stylized depiction of probability density function for the ERCOT grid. Basically, what this is saying is that if you just randomly look at the demand at any time of year in the ERCOT grid, this is the probability it will be at a certain point. So the most likely point is about there, which is about 35 gigawatts. And then you get this long tail. So this is really the issue of interest. And then if you look at all the generators and looked at their forced outage rates and combine that statistically, you get a generator availability curve. So this means that if everything's online and nothing is broken, there's over 100 gigawatts of available capacity, but there's a possibility there might only be 70 gigawatts. And so the area of interest is this overlap. So this is the probability that if demand is high and there's a lot of breakdowns, there may be what is called a loss of load. Now, in order to look at the trade-off between storage and the value it provides, I used reliability indices. So the approach I took was that renewable energy is used as a demand reducer. that's compared with the available generation. And unmet demand, I looked at the probability of unmet demand for every hour. And if we sum the loss of load probability for every day of the year, we come up with what is called a loss of load expectation. So this is the primary reliability metric used by most electricity systems in the world. Australia uses a slight variation on this called the unserved energy. And this is a result that I came up with. Now, really the main, I'll just describe it first of all. So starting from, well, first of all, what this does is it looks at the amount of conventional capacity that has been replaced in the ERCOT grid. So potentially, it would require replacing about 82 gigawatts of capacity in the ERCOT grid to have a 100% renewable system. And so if we would imagine doing that with wind, solar and storage, what would be the embodied energy of doing that? Now, one of the main conclusions of this is that we get effectively a parabola. So the first units are quite easy to replace with storage, but then there is a diminishing return. And this kind of makes sense. You could come up with this from an economic analysis as well. The main thing is that the first units of storage are the most valuable, but then there is a diminishing return. And it's partly because it's fairly easy to sort of fix this problem here, but as you push back, it becomes much harder. You need to be able to provide more energy. And so this provides a way of measuring the EROI of storage and comparing it to the value it provides. And so doing this for a specific instance, there would be some sort of optimal amount of storage. So this was a, unfortunately Josh Floyd isn't here. I co-authored this with Josh, and I'm sorry you can't see this, but I looked at the variation in PV studies and looked at all the factors that contribute to a divergence. So this is system lifetime. So basically, if you assume a system lifetime of 30 years, you get a higher EROI than if you assume 20 years. So that's pretty straightforward. One of the big things, though, was that the energy convention that you use, the IEA versus EIA method, basically you get that much difference. Oh, shit, what's... Oh, sorry, I'll go back. So basically you get a 3-to-1 difference. By simply assuming a different energy convention, you can either multiply your EROI by 3 or divide it by 3, depending upon which way it works. And one of the problems is that this isn't widely recognised in the literature. And this is something, well, it's partly due to goal definition. People have different goal definitions when they're developing an EROI study. And it's often not clear. If we're looking at energy transitions, we need to really understand how this works and which convention to use. This compares basically 2 different methodologies for life cycle assessment, process-based versus input-output. Basically, if you used an input-output, you basically get about half the EROI compared to process-based. Most studies use a process-based analysis. And that's partly because the traditionally LCA studies were about comparing different examples of the same technology. How do they compare, rather than trying to understand how they fit into an energy transition. I'll keep moving on. I won't go through the rest of those, but because I'm going to run out of time. Okay, so to lead into my final paper, I'm just going to use Australia as a case study. So this is primary energy consumption from 1900 up to 2016. We've got the main fuels. This is sort of a typical sort of graph that you see nationally. Then we can overlay real GDP onto that. This is the real GDP axis. So this is sort of a typical sort of graph. We see GDP going up with energy. But one of the interesting things is that during this period here that I've called the post-war industrialisation, we see this gap widening, which means that the economy was becoming more energy intensive. So this was a period of industrialisation, motor car use, expanding house size and so forth. I've labelled this period the service economy where we start to see this gap converge. So this is decreasing energy intensity or improving energy productivity. This blip here is a combination of things, rising electricity prices, the carbon tax and so forth. Now, what I wanted to do was link economic wealth with energy use. And so I'm going to introduce three terms. Y of t is GDP at time t, energy consumption and population. And if we do this, we get GDP per capita, energy per capita, and energy productivity. Now the E's cancel. Looks like a bit of a tautological equation, doesn't actually say much. But if we look at the changes, change in GDP per capita equals change in energy per capita plus change in energy productivity. So it's important that this is just an equation. It's not establishing a causal relationship, but it's one way to look to, well, to link energy and energy productivity. The importance of GDP per capita is that really from economics, this is the main figure. This is what drives this rising standard of living, rising income growth and so forth. If this number's high, everyone's pretty happy, governments stay in and everything's great. So what I did is that I took the data from that previous slide and I extracted the data and I've put it into decade blocks because it's quite volatile on a year-on-year basis. So the red line is GDP per capita and that equals the sum of these two columns. So we can see around war and post-war, per capita energy use increased substantially with declining energy productivity. And so most of our per capita GDP can be attributed to rising energy use. So remember, this is just a mathematical equation. It doesn't establish the causal relationship, but it's one way of looking at it. And so this is the rest of the decades up to 2010, up to 16. So really the main observations of these is that we see starting around 1980, rising energy productivity. So this corresponds with the Hawke-Keating years, shift to a service economy, and this is kind of what we expect. But the other thing is that we're also seeing declining rise in per capita energy, and in this period actually it was negative. So normally we would say, look, decline in energy use is actually a really good thing. But framed in this way, it's leading to a decline in per capita GDP. And this has become a huge problem. This is a sort of a global issue, secular stagnation, fall in income growth and so forth. There's a lot of stuff in the economics profession trying to work this out. No one's really looking at energy though, but this is one way to look at it. Now, if we think about a shift, if we look at outsourcing of energy intensive industries, what we would expect is that we would see a decline in per capita energy, but also a rise in energy productivity. So that should, in theory, sort of offset each other. So I did that to lead into this. This is a paper I just published where I tried to bring the biophysical perspective and consider it in reference to integrated assessment models. Basically, as we heard the other day from Zeb and Alex, integrated assessment models are driven by scenarios. One of the key drivers of scenarios is productivity growth and GDP. This is just considered an exogenous driver. Now, one of the assumptions of biophysical economics is that GDP is actually emergent out of the system. We can't just simply plug in an exogenous value. We need to understand the energy system first. So baseline scenarios project, well, this is from AR5, a 3 to 8-fold increase in GDP per capita by 2100, but with minimal consumption losses. So what that means is really we can, because we're all going to be really wealthy in the future, it really doesn't matter what we do. This is sort of an outcome of IAMs. And I discussed some of these issues. I won't go through it all, but what I end up with is a proposed preliminary model for using GDP as a feedback. If we look at scenario GDP, goes into the integrated assessment model. We produce a detailed energy system model and input-output tables. The main challenge is working out a transfer function that links GDP growth with EROI and energy cost share. But that is calculated, goes back into here with an error term, revise the energy system and start again. So I imagine this is an iterative process. The key is that GDP should be emergent out of the system, and we need to consider the EROI of the entire energy system in order to be able to make sense of it. So to sum up, and really this is the main thing, EROI provides an energetic valuation of energy supply technologies. Normally we think about an economic valuation, so I'm not advocating abandoning an economic evaluation, but we need to understand the energetic valuation as well, particularly if it's low. If it's high, it doesn't matter. We just look at the economics. So from an EROI analysis point of view, we need to establish the impact on the overall system. So nearly all EROI analysis look solely at the particular technology in the context of lifetime energy generated. But that doesn't tell us what the impact on the overall system will be. And basically, if the EROI is very high, and I've used a figure of 20 to 1, we really don't need to consider EROI at all. A conventional analysis is the appropriate way to go. But a lot of the energy modelling literature uses technologies that have a low EROI. I mean, one of the examples, as Roger said, is biofuels. So you can't assume that a model that's run in biofuels is going to be biophysically feasible. And it gets quite difficult with electricity technologies because everything has to work as a system. And prospective modelling needs to take account of the energy economic nexus because if it doesn't, it's simply not providing a full picture. Thank you.
Thanks, Graham. Cheers. Do we have any questions? Yes?
Thank you for your talk. I really enjoyed it. You had one comment in your key point slides, but at the beginning, that most of integrated assessment models have this characteristics that they are a closed system. So I wonder if you can shed a little bit of light what you exactly mean. The reason I'm asking is that I have done integrated assessment model for US for 6 years.
Yes.
But I haven't worked with IPCC model. I have worked with the Markov model, which US EPA uses, but we didn't have such a comment or, you know, kind of point on the model that is a closed system. So I wonder if you explain a little bit on that. And my second question is that in the slide that you showed the energy flows for your EROI calculation, I saw in your end use sector, you have considered only residential and industrial end use sectors. I wonder why commercial or transportation sector are not as a part of end use sectors.
Okay, thanks for your question. I'll answer the second question first.
Thanks.
The Australian Bureau of Statistics basically breaks everything into residential and industrial, and that's their categories. So some countries produce government, commercial, industrial, residential. That's the Australian statistics. So that's why it's split into those categories.
So it means that, for example, transportation sector is considered as a part of household, and then, or industrial sector contains commercial sector as well?
Well, there is transport attributed to the residential sector. I mean, your normal transport industry, that is industrial. But then there's domestic car use, which is residential. Onto your first point, the IAMs basically adopt standard economic assumptions. So production functions, capital labour, some of them put in energy, but they use, they adopt the output elasticity equivalent to the factor share. And so they don't adopt biophysical assumptions. And GDP growth is exogenous into the model. So it's just plugged in. It's kind of interesting speaking with a few people that some of these criticisms are actually known about, but this is the mainstream way that models work. So I'm not involved in the modelling community. So I mean, I'd be interested in your feedback too on what your sense is, maybe afterwards.
So a question from Anita, do you have a question? And then Malta.
Thanks, Graham. It's been a pleasure having you for the last 3 years, and your matter-of-fact approach to everything in life. You just see it as it is. So this is not my area, as you know. So can you just take a step back for me and maybe for other people in the audience and explain what is and therefore the difference between the process-based life cycle assessment and then the input-output? So what's the difference there in what you're doing?
Okay, sure. Well, I'll grab a pen. So with a process analysis, if we wanted to understand the environmental impacts or the embodied energy in the pen, we'd pull the pen apart, we'd look at the materials, we'd go to tables that would say, well, the plastic consumes a certain amount of energy. We'd go to the factory that produced that and look at the environmental impacts, material flows of that factory. And then we'd look at their supplies and then take the next step up. So that they have 10 suppliers, we'd go there, and then it becomes this thing where we just keep going forever. Now with process-based analysis, because that becomes very tedious, the idea is to just pick the most energy-intensive processes and focus on those. Now, an input-output analysis instead it might look at the pen industry and look at all the economic flows, and this way you get everything. So, for example, their phone bill. What is the embodied energy of the phone? Even though you don't actually have to know that, you just track those flows, and matrix algebra basically takes care of it because you get recursive flows and so forth as well.
But you have to do the whole economy to be able to do that analysis, but then you can focus in on the individual sectors.
That's right. You have to do the whole economy. Then you can then look at introducing other countries as well, and it gets more complicated.
Thank you, Graham. Likewise, it has been a pleasure to have you here in the college. Fantastic. Could you please go to the conclusion points? And I apologize as that question might be very silly, or you might have covered it. So please ignore that question if you did. The second last point, much of the energy modeling literature utilizes electricity generation and storage technologies that have significantly lower EROI ratios than the typical incumbent system. My question on that first sentence would be, storage technologies, how do you calculate an EROI, and shouldn't that be by design negative because it's not meant to produce energy, so you will always have a negative EROI? And then in those cases, the model system may be energetically infeasible, even though it represents a cost-optimized solution. Question on that sentence: if it's not a feasible system, then it can't be a cost-optimized one.
Yeah, thanks for the question, Malta. But this is a really sort of important point, and it's sort of one of the reasons why EROI is important. So I think the case of biofuels is really the easiest one to understand. You can put in a cost for biofuels, and you can optimize your model, and then you get a model that works. But if the EROI is, say, less than 2 to 1, the first problem is that you're measuring the gross energy flows. In fact, the energy you're getting out of the biofuels would only effectively be half of what you're modelling. That's the first thing. And society requires a minimum EROI of something like 10 to 1. And so adding the biofuels is going to decrease the EROI of that modelled system from what it would otherwise be. As far as storage goes, because storage doesn't generate energy per se, what it does, it lowers the EROI. Because EROI is a ratio, we don't think in terms of negatives, we just think of a smaller number. But there's obviously a trade-off, and that was one of the papers that I did, was trying to explore that trade-off. And so my sense is that some storage is worthwhile, but a system with, let's say, weeks of storage is just not going to be biophysically feasible. And that's part of the problem. I mean, that is part of the outcome of my thesis, that we need to think about how storage works.
The way I look at it, Monty, is the first PV panel, you don't have to worry about storage. So that PV panel has a different EROI to the last one that requires significant storage to facilitate its use in the economy. So not all renewables or variable generation are equal depending on the system that they're being installed in. So the storage has to be integrated with the generation technologies to understand the full system, the ROI.
Another way is curtailment versus storage. I mean, this is sort of an active area. Sometimes it's better just to overbuild the renewable energy and curtail rather than store. So that's a trade-off as well. But that can also be assessed from an economic perspective as well. You can assess it economically or energetically.
Okay. Hello, Graham. Okay, saving energy. Thanks, Graham. Excellent presentation and really a clear set of slides. Could you go back to the one with bar graphs on it in the per decade? That one there.
Sorry. Okay.
Now, it's clear you've said there's correlation, but there's not causality between GDP growth and the EROI. And in particular, when you look at the last 2 decades, can you comment? I mean, an ex-Prime Minister who you mentioned, Mr. Keating, is mentioned quite clearly where a large percentage of our GDP growth is coming in Australia, which is in immigration and migration. Can you comment on 2 of the macro factors? One is migration, and secondly, shutting down some of these very energy-intensive industries like aluminium smelters that are taking, say, 15% of our energy production, and how that fits into this GDP growth and, in effect, the ROI of what you're presenting here. Because I would argue that correlation is adjusted significantly because of those 2 macro issues.
Okay. Yeah, thanks for your question. So this is per capita. So population increases, you don't see population increases in these. And so there's the argument the government's like population increase because it increases GDP. even if GDP per capita isn't strong. So this is part of the motivation for strong immigration. The loss of energy-intensive industries, you know, I haven't done the analysis, but I think I mentioned you would expect a loss of, say, Portland smelter would decrease the per capita energy consumption, but also increase the energy productivity. So they would be offset somewhat, if that makes sense. So one would go down and one would go up.
Yeah, it's interesting. These, what you might call heavy consumers of our energy result, but very little real, what I would say, economic input to the national economy, or having the local economy. And then you're seeing a 15% shutdown of energy consumption. And if you go back to your slide, which shows the GDP as a function of energy consumption. Go back to your slide of really the amount of, I don't know whether it was in petajoules of energy consumption of Australia since the early century, I think, start of the century. I mean, it's a really interesting set of data we've got here. And in this period where this period between the red graph of GDP and the positive blue line there of...
So that is just simply the top of that curve with hydro and renewables at the top of the stack. So are you referring to the fact that this is widening here, yes, but then narrowing here?
In which I would, you know, I can sort of understand the top part, which I presume is because of this shutting down of these energy intensive, and also you mentioned the cost of energy and potentially a carbon tax.
Yeah, well, I mean, the cost of electricity doubled, so, and that was seen in black coal. But going back to the...
it's also energy efficiency as well.
Yeah. I mean, one outcome of, if I can get back to the bar graph, is that if we can make this even bigger, that basically gives us rising per capita GDP, rising productivity. So that's energy efficiency, basically producing more goods with the same amount of energy. So if we were to focus on that, then
there's a correlation, but the causality may not be there.
Well, that's right. Trying to dig into that is much more complicated.
And it doesn't have to be goods, it can also be services.
Yes.
So education, for example.
A really interesting piece of work, so good job, Graham.
Thank you. Dylan.
Thanks. Just quickly going back to Malta's question, maybe this is off the mark, but I think the difference there might have been Malta talking about technology-specific EROI versus system-wide EROI, in which case, yeah, it doesn't make sense to do a technology-specific, I would think, technology-specific EROI for a battery because of what Malta was saying.
Oh, okay.
Yeah, but could you just go back to that GDP versus energy productivity figure? I'm quite curious to know, you mentioned the sort of accounting issue around renewable energy in particular. I actually had a fairly detailed conversation with Alan Pearce about this exact problem on the retreat just the other day. I'd be very interested to know what do you mean by primary energy consumption in the case of hydro and renewables in this particular case?
Yeah, that's a good question. I did this graph ages ago, and whatever BRE do, I think I just use their data. But yeah, but that's a really good point, because if we multiply that by 3, basically that gets, you know, that goes up here. And so this is actually a really big issue, particularly when we're just looking at primary energy. Like if we look at electricity, it doesn't matter because that's all we're measuring. But if we're looking at primary energy, yeah.
So one of the, I'd be interested to hear your opinion on this, but one of the things we were discussing was the idea of actually using basically the velocity of wind and the energy per unit area as primary energy for solar, for example, which would be actually make it much bigger than a multiple of 3. It'd make, I mean, and that if you think about what the primary energy is, that would be the correct energy input to use, and then you do actually incorporate any sort of productivity gains or efficiency gains in improving solar technology or wind technology, and you would end up with a much wider section on that graph. But anyway, I'd be interested to hear what you think about that.
Yeah, well, it's a really interesting point. The life cycle literature uses CED, cumulative energy demand, as another measure. And so with solar, there's 2 ways to do it. It's called the energy harvested or energy harvestable method. Now, one method assumes that the primary energy is simply equal to the electricity that comes out of a solar panel. But the other, the energy harvestable, uses the total sunlight that's incident upon the panel. So if you're talking, say, a 14% efficiency, it's 7 times the amount of energy. And the way, and some life cycle assessment methodologies actually use that, and the same with wind, of course. But you can also get some anomalies, like in Europe, there's efficiency standards, I can't remember which one, but what can happen is if you multiply electricity by 3, it means that if you add renewable energy, effectively you're multiplying the effective energy efficiency by 3. So 1 unit of electricity reduces consumption by 3. And that may not be the intent of the efficiency standard. So it can kind of work both ways. I mean, my sense is that it's really more a matter of understanding the convention that's been applied and trying to work out how it fits into the goal of the study.
I suspect, I don't know, but I suspect BRE uses, might use the IEA approach, but I can't remember. But you see the mismatch or the incorrect comparison all the time.
Yeah, and people aren't aware of it is the main thing.
And then there's all the wasted primary energy that doesn't even hit a solar panel. Do we count that as well? Because that's lost energy, lost potential. Any other questions for Graham? Yes.
Yes, hi Graham. Sorry, this question's probably very simple relative to everything else which has come up, but I'm just wanting to see that graph. You called it the ERCOT graph?
Oh, ERCOT, yes, that was back.
So ERCOT is meaning the region of Texas, or is that the name of that?
ERCOT is the name of the electricity system, Eastern Regional something or other. Yeah, Texas, so, he's probably Texas.
And so that, would that be comparable to, say, the NEM? That sort of, if you took the midpoint of the demands, you'd have some 40 gigawatts relative to a generator availability. I mean, it seems to be quite an excess of capacity in a system relative to the demand at 99% of the time. Is that sort of similar factor? Is that in every grid in the world? It's not a particularly good or bad example in ERCOT's case?
Yeah, this is intended as a stylised depiction, and I've made that so that you can sort of see that gap. I mean, this is the typical shape of most large grids. You get this sort of large amount in the sort of mid-range, and then it tails down. Not often the tail will actually continue further. You get just a few hours of the year where it's right up. And that sort of bell-shaped curve, that's what you get when you get a lot of generators with independent outage rates. And you combine them, you basically end up with that type of bell-shaped curve. I mean, basically, yeah, that is the amount of surplus capacity that's usually applied, because we like reliable electricity. And I mean, you don't want to be in charge of a government where we don't have enough electricity. And so that's the way. I mean, this figure is something that we basically decide. We decide how much reliability we want. And we, as a community, we decide we want very high reliability.
But put one way, we might effectively have 10 gigawatts of power in the grid to save, as you mentioned, those 4 hours per annum of brownouts.
Oh yeah, well this is a huge issue. Roger can
yeah,
probably
yeah.
talk about
And
this.
the NEM does look very similar to this. There's pretty close to 50 gigawatts of capacity if everything's available, and the maximum demand if all 5 states are going at full bore on a hot summer's day is about 38 or 9. So there is a big gap between the two. That means the system should be stable, but of course, correlating with hot days is failures of coal-fired power stations, transmission lines, and so you still do get that potential loss of load when events conspire. Okay, we probably should let Graham off the hook. That's been a really good discussion session. So let's please join me again in thanking Graham for his presentation.